So as we look at this one, it's another example just like what I did where we just plug and chug. The only thing that gets weird here is sometimes the sig figs. And if I is not an integer, then it does have significant figures because it was determined through experimental values. Now let's look at something that's a little bit different using this idea of the Van Hoff factor. What's the apparent molality of a 1 molal acetic acid solution that freezes at negative 1.90 degrees C, and what is the percent dissociation? What is acetic acid, chemically speaking, acid-base speaking? Not the formula. What type of material is it? Acid-base speaking. It's an acid. What kind of acid is it? It's a weak acid. And what do we know about weak acids from their definition? They don't dissociate completely. They dissociate a little bit. So when we're dealing with something like a weak acid, we can actually use the freezing point depression or boiling point elevation or any other colligative property to figure out how much it dissociates. So first, we're going to calculate the actual change in freezing point. So we know that this is an aqueous solution, and we know the freezing temperature is negative 1.90 degrees. So delta T is equal to the normal freezing point minus the freezing point. So that is 0 degrees C minus a negative 1.90 degrees C. So my change in temperature is 1.90 degrees Celsius. And we know that delta T is equal to K sub F times M times I. And we said that these two variables together, Mi, is equal to the apparent or the effective molality. So delta T divided by K sub F is equal to Mi, and I'm going to just keep them together and solve for that as one variable. Mi is the effective or apparent molality. So my change in temperature, 1.90 degrees Celsius, divided by my K sub F value. I actually have a place to go through this stepwise on the next page. Okay. So calculate the apparent molality. 1.90 degrees Celsius divided by 1.86 degrees C per molal is equal to 1.02 molal. Now, the information for this problem said that it was actually a 1.00 molal solution, but I'm seeing that it acts as though it's 1.02 molal. So this gives us 0.02 molal of extra particles. So we subtract the given molality from the apparent molality. This is where it's a little weird that you have to look at this and think about it. I have a solution that acts like it's 1.02 molal minus what I mixed up with the compound, 1 molal, is 0.02 molal, and I'm going to call this extra particles. So if you think about it, that acetic acid has dissociated a little bit. That's not an N, that's an H. It's dissociated a little bit to give us that proton plus the acetate ion. So we get one extra particle for every molecule that broke apart. Now, if we think about this, I have 0.02 molal of extra particles divided by my original concentration, 1 molal, times 100 is 2% dissociation. So a different kind of problem than what we've worked up until this point. So now just take a minute at your seats and do this same calculation. Find the percent dissociation in an aqueous solution of 0.125 molal monoprotic acid that freezes at negative 0.261 degrees C. So you're going to do exactly the same thing. Calculate the apparent molality, subtract, and then go ahead and find the percent.